Welcome to the Explainer. Today, we're diving straight into the mechanics of data preprocessing, specifically feature scaling. We all know that raw, messy data can easily hijack a model's performance, right? So we are going to break down exactly how standardization and max-min normalization step in to level the playing field.
Here is our roadmap for today. 1. The feature scaling problem. 2. Defining the solutions. 3. The math made simple. 4. Standardization versus normalization. And finally, 5. When scaling actually matters.
Okay, let's jump right into Section 1, the feature scaling problem, a tale of two variables.
In the real world, whenever we crack open a dataset, we constantly run into variables with wildly different ranges. Just imagine a standard dataset predicting whether someone bought a product. You've got independent variables like age and salary. Age has this tight, modest range, say 27 to 50. But salary, that can easily swing from 48,000 to 83,000. That range is absolutely massive compared to age. They are literally just not on the same scale.
So, here's a critical question for you. When you feed these original, untouched scales into your machine learning algorithm, which variable do you think completely dominates the outcome? Well, if you're guessing the one with all those extra zeros, you are absolutely on the right track. Let's look at exactly why that happens under the hood.
The big thing to understand is that a lot of machine learning models, things like k-means clustering or nearest neighbor classification, rely heavily on calculating Euclidean distance. And if you think about the math there, the square difference between two salaries, those massive numbers in the tens of thousands, is going to be infinitely bigger than the square difference between two ages. The sheer size of those salary numbers will just unfairly shout over the differences in age. Without scaling, the age differences contribute almost nothing to the overall distance. Using the original scale just puts a massively unfair weight on whichever variable happens to have the larger range.
Moving on to Section 2, defining the solutions, the great equalizers.
To fix this and level the playing field, we use feature rescaling during our pre-processing phase. The goal is super simple but incredibly powerful. Force all those features onto almost the exact same scale so every single one gets an equal voice. First up is standardization, which is sometimes called z-score normalization. What this does is rescale your features so that the mean of the data is exactly 0 and the standard deviation is exactly 1. This technique is an absolute lifesaver for optimization algorithms that weight inputs, like gradient descent in your neural networks.
But then we have the alternative, max-min normalization or min-max scaling. Now, people sometimes mix these terms up, but they are definitely different tools. Max-min normalization rescales features strictly so that every single value fits neatly within a distribution between 0 and 1. And the great thing here is it doesn't require you to make strong assumptions about the distribution of your data. It just transforms those varying scales so no single dimension can dominate your statistics.
All right, Section 3, the math made simple, max-min normalization.
Let's break down the logic here, because it's actually super elegant. It boils down to 3 straightforward steps. Step 1. For every feature, find the absolute minimum value and transform that exactly into a 0. Step 2. Find the absolute maximum value and transform that exactly into a 1. Step 3. Take every single other value in that feature and scale it proportionately right in between that 0 and 1 boundary. It's neat. It's bounded, and it totally eliminates that issue of a massive salary range overpowering a tiny age range.
Section 4. Standardization versus normalization. The head-to-head clash.
When we compare the two, max-min normalization actually gives us smaller standard deviations compared to standardization. Your data becomes highly concentrated around the mean. Standardization, on the other hand, leaves the data a bit more spread out with its standard deviation of 1. But the real kicker? Look at how they handle outliers. Normalization handles them poorly, while standardization handles them robustly. So why exactly is that?
Well, this is basically the ultimate kryptonite for max-min normalization. Since you are forcing every single data point into that incredibly strict interval between 0 and 1, think about what happens when you hit a massive outlier. Let's say just one person in your dataset happens to have a salary of $10 million. Boom, that $10 million becomes your 1. Suddenly, all of your normal, everyday salaries, the 48K to 83K ones, get totally squished together into a tiny fraction of a decimal near 0. Normalization basically compresses most of your data just to accommodate that single outlier. Standardization doesn't have that strict 0 to 1 ceiling. It absorbs them. It allows you to handle those anomalies without completely destroying the variance of your normal, everyday data.
Which perfectly brings us to our core takeaway from the source material. Quote, Standardization is more robust to outliers, and in many cases, it is preferable over max-min normalization. End quote. Because let's face it, real-world data is almost never perfectly clean. Standardization just gives us a safer, more reliable baseline that also helps computational algorithms, like gradient descent, converge much faster.
Section 5. When scaling actually matters. The algorithm cheat sheet.
Okay, here is a bit of a secret. You actually don't always have to do this step. Let's start with where it is absolutely non-negotiable. If an algorithm is fundamentally based on a distance matrix, which we call distance-based classifiers, feature scaling is completely essential. We're talking k-nearest neighbors, support vector machines, and neural networks. Just like we talked about with Euclidean distance, if you skip scaling for these models, the variables with the largest numbers will just blindly dictate your math and completely ruin your accuracy.
But on the flip side, if an algorithm is not distance-based, feature scaling is honestly largely unimportant. Take models like naive Bayes, linear discriminant analysis, and tree-based models like random forest or gradient boosting. These algorithms make their decisions and splits based on the rules within individual features, right? Not by comparing the numerical distance between different features. So if you're spinning up a random forest, you can actually just skip the feature scaling step entirely and save yourself a ton of processing time.
And that brings us to the end of today's explainer. We've seen exactly how wildly varying data can completely hijack an algorithm, how standardization and normalization swoop in to fix the scales, and precisely which algorithms actually demand this kind of attention. So I'll leave you with this. Next time you sit down to build a model, will you just let your loudest variable dictate the outcome, or will you use these mathematical tools to level the playing field and let the true patterns emerge? Thanks so much for joining me on The Explainer. Keep learning, keep building, and I will see you next time.